Hi there viewers, this is Mixer91 and welcome back to watching Pokemon Gold and Silver and Game Boy hacking tutorials, and this time part 7 of them. And today I'll be explaining that long-awaited code for building that counter for the Fat Man. And for starting out, we'll actually be doing some other things, but well, the plan is like this. Here, first, I'm going to show you the script, which introduces two different things: a loop and a subprogram. And the plan is to build an event which replaces this current script here. That makes the Fat Man give you a Magikarp, and if you refuse, he will tell you why not. And this thing loops all over and over again until you are indeed given the Magikarp. He says, here you are, and if you don't have room for it, he also checks that. But yeah, let's start out. And we don't have to I could go ahead and delete all this in the ROM with a hex editor, but you know how to do that, so I don't bother. But first of all, like every time he has to face us, load font, tell us that I just fished a Magikarp, would you take it? And then there would be a yes or no box. And well, if we say why not, it has to. Well, if we say no, he has to tell us why not. So that has to be some different code where he says that. So a different part of the main code. So if we, for example, do it like this. Now if we now here he tells us that he fished the Magikarp and should we take it. And if we say no, here he tells us why not. And well, why not? And then the another yes or no box should appear, because now we can also say yes or no. And well, if we say yes, it could be like this: if true. And well, yeah, if we say yes, it should go back to the main script. How should I explain this? Well, the thing is like this. Let's just ignore what we have right here for now. So here first, he faces us and tells us he fished the Magikarp. And if we don't want to take it, the script continues here, where he says, why not? And if we say yes, which is checked with if true command, it should actually get back to the main script data. Because if we here said yes, we want him to execute the same code again. The same code for giving us the Magikarp. So with this if true command, we actually want to jump here to the command after this if false. And well, here face player is in this offset. Load font is 1 byte ahead in 1, 1, 2, 5, A3. This is A4, A5, A6, A7, 8, A8, along with the false is in A8, A9, A9, and AA. So this load move sprites here is an offset 1225 AB. So if I adjust it like this, now this, if we want to take it, it jumps here. And that's what we want to do. And if we don't want to take it, he should tell us why not. So in case of if false, we could do it like this. So now, if we don't want to take the magic orb, we jump here, where it tells us why not. Then he also, the yes or no box also appears. If we want to take it, it jumps here. If we don't want to take it and say no, it loops back here. And here we have a loop now. Loops work so that there is a certain condition, and if that condition is met, the loop ends. And this is checked for ending the loop. So if the condition is if yes, the loop ends. And if we said no, the loop starts over again. So it loops all these 4 commands in an order until we tell him yes. And this is how it goes. So if we check it here, compiling it, you can see that it works. This load move sprites, or this code here, is the same as what we've got right here. So when we want to edit this, we actually want to ignore this part like this. So when we compile it again, it compiles properly in the ROM. So in case of we want to take the magic orb, which is right here. Now he should tell us, here you are, and check whether we have room for it. So there is this one of these check code commands that is used to check the amount of Pokémon you have in your party. So I'm just going to use that. It's 1C code 01. Check special game technical values and writes them into RAM. So we put check code 0x1 here, and it stores the amount of Pokémon in our party into RAM. And if we have 6 Pokémon, this is code 0x6. My RAM is byte 0x6. We go somewhere. For example, if this is in C25CO, C1, C2, C3, C4, C5, C6, C7, C8, C9. Did I count correctly? I guess. We could put it in already in 65CA, or if we want to leave a bit of room, we could put it in the code here in 1225DO. So if we don't have room for the given magic carp, he should tell us that I'm afraid you don't have room for it. And as you can see, here we have write text code without keep text open. So I want to put keep text open here first. And following it, we have this write text. If no room, oh, I'm afraid you don't have room for it. And then it could close text, load move sprites, and end the script data. And in case we have room for it, I'm actually going to do this. I'll put this a little bit ahead because I'm not sure if I ran out of room or not, because this is in A2 and I'm putting more and more stuff here, so it could easily overwrite data in 1225CO later on. So I'm just making it sure that won't happen. And we won't go this far. This code won't be so long it would overwrite something in here, so this is okay for having this data right here. So we tell here you are and see that there is room for the Pokemon. So now we use a give Pokemon command, and let's just see how it works. Hmm. 2D code. Gives a Pokemon if there's space. Gives trainer ID as feedback. Ah, we actually don't have to. Well, we can build it like this, yeah. But we actually don't have to, because this also checks where we have space in our party. But, well, with this code, we can make him print this text string that you don't have room for it, if we don't have. And give Pokemon code actually works also so that it stores the given Pokemon in PC if your party is full and there's room in the PC. So this works differently now. But we adjust the first value as the Pokemon number. And actually I happen to remember by heart that the Magikarp is 81. Hopefully I'm correct about this one, but I think it's 81. And let's just say Magikarp will be level 5 and have no item. Item number 00 is no item. Or nothing. And then the trainer, well, we can adjust the trainer as 00 for making the trainer the player, or we can change that into 01 and this will work differently then. I think after this, if we put 01 here, we have to adjust 2 pointers here, like said here. Like I said, 2 byte pointer to trainer's name and 2 byte pointer to nickname. So with 01 it would work like this, but without it, this works as well. And now the given Magikarp belongs to the player, or has the player's trainer ID. And after this, we want to set some bit that marks that this event has gone through already. And well, I'm going to use bit number 0x48 for instance, and the script will end, because this here ought to work. And I actually want to use close text code between the give Pokemon code, because, or maybe actually keep text open would be better in this case. So we could put this keep text open code here, and remove it here from here along with the close text, because now we keep text open before checking if we have room for it. So text box is kept open, and after I think give Pokémon command closes the text box while at it, so this ought to work. And order between these two doesn't really matter at all. But yeah, this is how you could build it. And finally, we put some check bit command whether this event has gone through already. If true, 65 FO, and here he can tell us that we got the Magikarp already, or be proud of what you got. And compile it into ROM. As you can see, the script data starting at here takes 23 bytes, so we could adjust the data following it in 1225 C5 or behind it. And now this ought to work, except for the fact that this if true command here doesn't point to the right data of the main part of the script anymore, because we just put this check bit along with if true here. And I'll explain this a bit later. Hi, I'm back. I was basically 2 hours away doing non-hacking related stuff, but I pretty much remember everything I was talking about earlier, so we won't have to have a problem continuing from here. So yeah, the last time when I checked this before, I finished this main part of the routine and the loop here. So yeah, it loops back to asking why not if you say no, and if you say yes, it should return from the loop to the offset where this loop started, or the offset behind it. And here we are with the first yes or no. Yes or no box. If we choose no, it goes to this loop, and we should return from the loop here to this code. And currently we're returning to this address right here, and you can see that load var stands for command with the byte 15. So this is actually the byte right here, and you adjust a byte to load var command. It's here 28. Well, I'll just show this so it makes more sense. So in 1225 AB we have these 2 bytes. 1225 AB we've got load variable in the RAM and variable 28, and then there's yes or no box, and then we have this if false and 2 bytes and this text data code. So basically instead of returning here, we actually want to return to this address, and you can see that it's 1, 2, 3, 4, 5 and 6 bytes ahead of this one, which makes sense because it worked before we added these commands here, and this takes 3 bytes, and this also takes 3 bytes. So yeah, 6 bytes. It has to point to 6 bytes ahead, and if you add 6 to AB, you get B1, I think. I'd say B1, yeah. And if we do this and compile it again, it should work. Yeah. Now you can see that we are indeed returning to this same code here, which is a good thing, because now this works. Now this works the way intended. And I could also adjust the text strings to the code, but I'd rather not do that because it's really not worthy of doing. Yeah, I don't think I'll do that, but I'll just show this in the game and let you know that it's working correctly. So we return here and talk to the fat man. He should face us and print yes or no box. Like you can see, it works. If we say no, it prints the box again. Here it goes through this loop, and until we say yes, he prints this text data, keeps text open, checks whether we have 6 Pokémon. If we have, he prints this data, and if we don't have, he gives us Magikarp. And well, there was no sound for the given Magikarp or anything like that because we're missing code for making the player to receive a Magikarp playing sound and that kind of stuff. But it works, as you can see. And now this bit was set, and if we talk to him, the text data, this code here is executed, which makes him face us and say object event. And you can see that this is probably bit 0048, which this stands for. Wait a minute. Yeah, 0048 or 4800. This code here is 314800 written in the ROM, and it probably sets this bit here. So if we reset it, yeah, that's what it did. It set this bit here, and if we say yes to this command here, the same thing happens, and we get a Magikarp, and this bit here was set. And if we repeat it long enough, we have 6 Magikarps eventually. And I also had a Cyndaquil at the start for, well, yeah, I did. I did have a Cyndaquil from the start, but now he shouldn't be giving us the Magikarp anymore. Yeah, because we didn't have room for it, so it executed what was there. So as you can see, this is working correctly now. First he faces us and tells us, I just fished a Magikarp, would you take it? If we don't want to take it, he keeps saying why not until we say yes, and then he says here you are, and gives us the Magikarp if we have room for it, and if we don't have, he says, oh, I'm afraid you don't have room for it. And the bit is set, and when we talk to him again, this script data here is executed for saying be proud of what you got. And it works. And well, yeah, this works just fine in the game. But the problem with coding like this is the fact that every time we add code before this toWrite text here, where we're jumping from this loop, which is right here, we have to adjust this pointer, because if we don't, it won't point to the right address. So that's kind of a problem. If we, for example, wanted him to do something like some showy mode code, I don't really know if this person event number matches with that fat man or not, but if we wanted to do this, this would have to be adjusted 4 bytes ahead to 65B5, because this takes here 4 bytes. And I already introduced you how loop works. And quite often when we are using loops, we actually want to call them instead of jumping to them, because here we are jumping to a loop. But instead, we would probably want to do something like if false, call this address. But because if we call the loop, and when we say yes inside the loop, we could return to this address here without having to jump to it like we're doing here. And that would be convenient, because that way we wouldn't have to worry about modifying the main script data. That is that this loop's eventually going to... Well, yeah, that way we don't have to worry about modifying the main script data if we're calling the loop instead of jumping to it. But we don't have such method such as if false call some routine. So that's a problem. But we do have toCall method, which used to call a subscript. And if we implement the yes or no box along with the possible if false command and if true commands in a subscript, and return to this address, or return to executing this code after the subscript ends, that would work. And that's what I'm going to do next. So I'll modify this code here at 1225EO totally. So first, I'm actually going to take these off. So in this call command, before this call command, he says, I just fished a magic carp, would you take it? And right after the toCall, or the subscript ends, he would say, here you are. And that's how I'm going to implement this. So let's delete all we have here, and we don't have to worry about this either, because we're never jumping anywhere. We're now executing data after the call code. And I'll take this out too, because it will only confuse people if we have unnecessary stuff going on in the background. So we call a subroutine or subscript that is used for the so-called yes or no loop. And in the end, beginning of it, I want to put the yes or no box, because it has to be executed after this command, which was used to tell us, I just fished a magic carp, would you take it? And to-call commands work so that the subscript ends with end command every time. You have to end it with end command. So what I'd like to do would be sort of similar to if true here. Could do it like this. If we build a loop inside the call, now it returns from the loop if you say yes. And if we say no, this here now prints text data. Why not? So here we had would you take it? And here we have, here we are. And the text string that goes with it. But yes, first in the call we want to use the possible check for returning from the loop. And we return from the loop if we say yes. If you say why not, if we say no, it prints why not, and then we only have to jump back to the loop. And now it works. Because we're calling a loop. Now we're calling a subscript that is a loop. And if we say yes, it returns from the subscript with end command. And if we say no, he says why not, and jumps back to yes or no box. And if we decompile, you can see that the script data is much more efficient now. And this here actually doesn't work anymore because it's in the same position as where you have this one. But if we, for example, adjust this back to jump text face blur 0x2815, where this is used to point to, and put this one in like 65.5 EA, this encode. Let's just count E0, E1, E2, E3, E4, E5, E6, E7, E8, E9. So in EA we have room for this encode. And compile it. And now the script data looks way different, but actually works totally the same way as before, as I'm going to show you now. So first, he faces us, loads font, tells us, I just fished a magic carp, would you take it? Then he calls this loop, which first calls for the yes or no box, which we see here. And now it waits for us to say yes or no. Now if I say no, he says this write text, which was used to why not, and it jumps back to the loop. So here, printing the yes or no box. And you can see that the effect is totally the same. And when I say yes, it goes to end and prints text data here. And the subscript ends, and text data here is printed, and he gives us the magic carp, like previously. And now this bit was set, so it just says object event by executing this code here. But yeah, knowing how to use loops and subprograms or subscripts can totally come in handy, and we'll be dealing with them quite a lot in the future, especially with assembly examples. And they're of course implemented in different ways in assembly language, but the main idea is totally the same. So at the end of the loop, we jump to the beginning of the loop, and in the beginning of the loop we can have some sort of code for ending the loop, like here, or stuff like that. So the normal execution of a loop is that we go through some routine until a certain condition is met and the loop ends. And this is one possible way of doing a loop, but in the following example of this counter which I'm building, the loop will be quite different, but the look of the loop will be quite different, but it will still loop a certain routine until a certain condition is met. So yeah, this is pretty much, well, yeah, this is how this works out. And I'm back from another recording break, and right now we'll start building the counter, making this fat man here count all the numbers between 1 and 1000. And for doing this, the most of the stuff is done with scripting. But before moving on to writing the script data, I'll just give you an example of, or not an example, but an explanation of how it's going to work. So I have actually built the code here, but in the beginning of it, this is also, yeah, it's a loop example. But in the beginning of it, we have this code for script data for making him tell us that he's the world's fastest man at counting numbers, and he can count all the numbers up to 1000 in under 100 seconds. And we could move all this data here in the beginning and start with it. This time I'm not going to stuff such as this one. I'm really not going to write in the ROM because that's not necessary, but I'll do write the code for or the text data for printing the numbers. That I'll do. So the main part or the beginning part of the script doesn't have to be anything this longer, and it takes 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 bytes. So I could, for example, adjust the next part 16 bytes ahead, or in hexadecimal 0x10 bytes ahead. And how this is going to work? Well, actually I'll show you this before. So we have this in-text code, code 09, for writing numbers from RAM in decimal format. And we tell us the RAM address or the pointer, they're the same thing, to the data. and following in the structure we have a byte that is split in two halves, so in two 4-bit halves. The first half is telling how many bytes to load, and the other half number of figures of displayed number. So we could have this as 0 because we really don't care how many numbers it displays. We could actually set it at the highest to 4 because 1000 is made of 4 numbers, and that is the highest digit our counter is going to give. And for number of bytes to load, well, it's going to go on like this. We have one RAM address, which I'm going to use as D004. Or actually we have two RAM addresses, D004 and D005. And in both of them we have a 1-byte value, and this one stores the ones and tens, and this one is storing the hundreds in a way that like 00FF would be 255 in decimal presentation. 0101 would be 257 in decimal presentation. 01FF would be 511 in decimal presentation. 0200 would be 512, and so on. And 1000's presentation would be 03 and some value which is quite close to FF, but I think it's E8 if I remember correctly. 03 E8 would be presenting 1000. And the main idea is building a counter that with assembly we have this increment instruction which is used to increment the value. So we'll be incrementing the ones and tens up to FF, and after FF, when we increment them again, here, increment register n, flags affected, set if result is 0. So we load, for example, well, we can load HL with the value in D005, and we increment the value in HL. And if Z flag is set, we know that the result here was 0, 0, and then we want to decrement register HL. So instead of HL holding D005 as its value, it's holding D004. And then we increment HL. So if we have, for example, 00FF here, we increment HL, Z flag is set, we decrement register HL and increment the value of HL. So after this one we get 0100. And we're building a certain loop that does this after until 03 E8 are the values in these two RAM addresses. And this is how the counter is going to work. And it kind of sounds difficult at this point, but it won't be that bad. But for starting out, so we need these two RAM addresses to hold 1-byte values for the decimal number presentation. That is written with this in-text code 09. And along with them, I'm using bit number 0000 for checking inside the loop whether the loop should end or not. And this bit is set if the values here are 03E8. Well, you'll get the better idea soon. It kinda sounds confusing at the moment, but it won't be that bad. But for starting out, we want to clear this bit number. Set it to 0 so that the loop won't end right away after printing the first number. And then we use write bytecode, which works so that we adjust the RAM address and the byte with it. So here we put the RAM address and what we want to write there. I think if PKSV works in a way I'd like to see it work. It might be so that we have to first write 0x0 and then this one for it to compile correctly, but we'll see. And B2, B3, B4, as you can see, this is actually like this, but you can write it as 0x0. This is in B2, B3, B4, B5, B6, B7, B8, B9, BA, BB, BC, BD, BE, BF, I think. So we can build the code or the main code here in 1225CO, and I'll put end there to see if this works. Value must be integer. Yeah, we have this thing here. And it probably works correctly. So he tells us he's the world's fastest man at counting numbers, and can count to up to 1000 in under 100 seconds. If we want to hear, he goes to start, which is this one, this code here. And if we don't want to hear, he just says "or" and the script ends. But here I want to build the code for making him he first says the current number. Yeah, it works like this. Then he then the value is incremented if 0 flag was set. Value in D004 is incremented. And if D004 holds the value of 03 and D005 has the value of E8, we want to set this bit here for ending the loop. And next we check this bit value. If it's false, we go back to the loop for displaying this number, incrementing it. We actually want to increment it first. Let's put this in different order, so it actually works better. So first we increment the value or the number. If zero flag was set, value in D004 is incremented. And we display the current number and check the bit value, and if that is false, we go back to the loop. And that bit value is set if both of these hold the right values, 03 and E8. And this part 7 will be executed only if the counter has reached the value of 1000, or both these values are 03 and E8. And then he can say the text string, see, I told ya, like in the video. And the script ends. Load move sprites and end. And that's how it's going to be. And let's just write this down here. And I'll take it out from here. So we have the code in this text document. So first, we have to do this kind of stuff. And I'm actually going to implement all of this with assembly. Although this setBit command could be done with scripting, but if we did, we would have to be doing something like we would have to with both of these values in these addresses, we'd have to write their values in the ROM and then check them whether they equal or match with 03 and E8, and if so, we would set bit 0x0, and that wouldn't be convenient because we can build that check inside the ASM routine. So all of these three we built all of them inside the same ASM routine for incrementing the value, and if that value matches with 03 E8, we set bit 0x0. And this bit set command is quite easy because we know that bit 0000 is in RAM address D7B7, and it's actually the bit that affects. It's the first bit in D7B7, and in assembly we can set it by load HL with D7B7 plus it's one of the bit set commands which we have here. Set bit B in register R. So we load HL with D7B7, and then we set 0 in HL. This is how it would work out. This can set that bit in RAM address D7B7, which is the same thing that is gone through if we use set bit 1 0x0. And why bit 0? Well, that's because in assembly we write them in a way that the first bit is the 0th bit, second is the first, third is the second, and the 8th bit is the 7th bit in this language. So if we want to set the first bit in this address, we have to use set 0 in that address. But yeah, let's start with building the ASM routine. And we have this script command for calling an ASM routine, and this 0e code is 3call ASM, and we adjust it with with a 3-byte pointer, and I'm, for example, putting the ASM routine in ROM address 27 multiplied by 4000. This is the pointer 270040 in the ROM, and it points to like I've told earlier, it works this way. So this thing points to 9C000. So we call that ASM routine. Then we display the current number, and we use this display text code for this one. In text code 09. So instead of actually printing object event, we want to print a number from the ROM. And now we don't want to use keep text open or close text, and that is because well, then we would have to require the player to push a button between the numbers, and that would be not very convenient at all. Besides, because he's counting numbers, and he's the fastest man counting them, there may not have to be anything slowing him down. Well, yeah, we want to check inside the ASM routine. We set this bit if these values are correct. So we have to check for the bit here, and if the bit value is 0, we go back to the loop. And when this thing ends, we may actually keep text open. And here he would say, "See, I told ya." And the script ends. And this is all the script part actually. And well, besides from these, I'll put pause 0x2 code here, and this for making the game to wait for a short period of time. So that's because of this thing going on so fast without it, that we may not actually be able to see the numbers it prints in the screen at all. Because it actually doesn't print the numbers right away after this command is executed. It takes a little bit of time for the game to access the a possible moment of writing the graphics. So if we try to write more text in the screen before this a short period of time is has expired, well, it won't work without this waiting for a short moment of time, a period of time. So we have to pause the game for a little while before printing new text data, because this really goes on very fast. There's nothing slowing the process down. It counts the numbers it counts them very quickly, even with this pause command here. But yeah, I'll just move on to building the ASM routine first. And for doing this, I have this Game Boy assembly editor I'm going to use. And this is a tool you can download in romhacking.net. So you can just go there and find it for yourself. And on the left, you can see the addresses in form. Here we have the ROM bank and the ROM address. And next to it we have what is written in that address, and that thing in as ASM instruction. Yeah. This is an assembly presentation of the ROM, or ASM instruction presentation. But I'm not going to explain how to use this editor probably as of now, but instead I'll just move on to editing the ASM routine. And we have put the ASM routine in this address, which is 9C000 in ROM file, as you can see. But yeah, and nop is a command no instruction performed, so it actually doesn't do anything instead except for slowing down the process of executing code by one instruction, but it doesn't really do much. Well, yeah, we want to write this code for doing all this, and the code must end with return instruction, RIT. And well, I'll just open that ASM instruction command guide again. But first of all, we always want to be modifying data here in D005. So we load HL with D005 by doing this. Right click the knob, right click the address, use change instruction, and here I can pick up something or write something on my own. And this is actually what I'm writing. Load HL with D005. And the increment works so that we can increment either a value in an address of HL, or we can increment value of a register. And I want to be incrementing the value in HL, and you can write it like this. So now this code increments or increases by 1 the value written in RAM address D005, and the routine must end with return code. And here I'll use instruction return enchat. And there are 3 different return codes. We have return, return chat, return enchat. Or we actually also have return C, return NC. But these all work so that we return from this ASM routine that has been called elsewhere if certain conditions are met. And this thing here tells that we return from this code if chat flag is not set. And this increment code sets chat flag if result is 0. And if the result is not 0, it resets it, which is not described here, but that's what it does. If it affects the 0 flag, it always either resets or sets it. And 0 flag is set if result is 0. So if we increase this value and it goes to 0, chat flag is set. And that only happens when this value is FF. If we increase FF, we get 0, 0. And if that value is not FF, we increase it and return with this code. And this thing here is only executed if the result is 0. So next we want to increase the value in D004. And for it I'm going to use decrement HL, this code here. Because, well, HL holds the value of an address, and this code is used to increase the value written in that address. So it increases the value in D005. But this code here, decrement HL, without these marks, it decrements or decreases by 1 this address value. So that turns into D004. So after this code, HL is set to D004. And we want to increase HL. Because now we're doing what we want. We are increasing the value in HL if needed. And that is good. And, well, yeah. Now we can, well, this kind of code, we can increase this value, and if 0 flag was set, increase this value. But there's a problem with this code, because we want to check for this condition, kind of a condition. And, well, instead of putting this red enchat here, I actually want to do something else. So we still want to use these instructions, but not just yet. So I'll knob them off. The problem with this assembly editor is that I can be for read-writing data between the other data. I have to delete them to do that. But we increase this, and instead of using a return here, we actually want to check if this value matches with E8, because then we have to check if this value matches with 03 and set this bit. So I actually use a relative jump and put this point. No. This can be quite hard at the start, but you'll get used to it in practice. So like I explained before in the earlier part, a relative jump I can also hold well, yeah, you can see here. If following condition is true, then add n to the current address and jump to it. And here we're adding 1a to the current address and jump to it, which is this one. And here I'm using if jet flag is reset, we jump here. And this code here is actually for checking if this kind of condition is true. So what I want to do, I want to load the value of HL into register A, because I want to use compare function, compare instruction. And we can't compare HL with something, we can only compare A with something. And here I want to compare A with E8, because we are loading the value in D005 into register A. And this thing sets 0 flag if A is N. So if this value in D005 is E8, 0 flag is set. And here I can actually use this ret enchet, because we have already incremented the value in this address. And if that is not E8, then we can return. But if that is E8, I want to check if the value in D004 is 03. So I decrement HL, and again load A with the value in HL. And after this, we want to compare A with 03. Because now HL, after this one, HL holds the address D004. And we bring the value of D004 into register A and compare A with 03. And again, if A was not 03, so in this case A is either 00, 01 or 02, we return. But now if A really is 03, we have reached the end of this counter, because the value in D004 is 03 and the one in D005 is E8. And then the decimal value is 1000. I think 3E8. Yeah. We have reached the end of the counter. And now we do this. load HL with D7 B7 and set 0 in HL. So now this instruction set here does this, set bit 1 0 0, and now we can return back to the main script that was called with recall ASM instruction command. And well, if this value, if here chat flag was set, we have to decrement HL, because this part here was to check whether the tens, well, this one here, if we increment FF, we get 0 0, and then chat flag is set. Then we want to decrement HL to D004 and increment HL, and then we can return. And this should be the whole ASM routine. These things here are not used at all, and I could also move all of this ahead, for instance here, because or already right here, or in 27 4010 or whatever, because now we're wasting space for no reason. But that is actually a good thing to do that when you're editing ASM routines. And now if I was to make this myself, I would have actually changed this instruction to work with this decrement HL as 1. There's this instruction such as this one, LDDA with HL. This thing is called load and decrement. So it first loads the value written in this address like we do here, and after it decrements HL. So we could actually combine these two together if you wanted to, but that's not important. Well, I'll just save that to ROM, and I'll let you see what this thing looks like in hex, and we can actually edit the code with a hex editor as well. So this thing was in 9C000, 2905DO, and so on. And return is here. And this thing here is all this useless stuff. And this code here is what we chunked to. And I could move it ahead if I wanted to. So like this load A with HL. Here we have compare A with E8, CO, 2B, 7E, FE, 3, CO, 21, D7, CB, C6, C9. And this actually tells where relative jump takes us. So I've changed that into 0A. It actually takes 10 bytes ahead of 40, 20, like we had it as before. But yeah, this is now the same code. written here, and it should work. I'll let you see what this looks like in the game as of now. So our script already should already work, because only thing it's not doing is printing the numbers correctly. But it should go through this loop 1000 times, because it only ends if these two values match. So if we talk to him, I'll just let you see with the memory viewer. So let's open D004. We can actually see that we have two numbers here, 9b and 01 as of now. So it would be kind of bad, or really bad, if it didn't write these things here. But because it does, well, it never asked the yes or no box. So let's just fill that in while at it. And we should also have room for it, of course, yeah. It says object event, and if we say yes, these numbers here should start to be incremented. As you can see, that's what it does. And it prints text data and checks whether this bit here is set. If it's not set, it loads HL with this value here. It increments it, what it's doing here, and checks whether the result was 0, 0 or not. If it's not 0, 0, it converts that value into E8. If that doesn't match, it returns. If that is E8, it decrement HL and checks what this value is. And if that value is 0, 3, it sets this bit. So, here's how it works. Now instead of printing numbers, he actually sets object event. And you can see that it works totally fine even when checking the case of A being E8. Soon enough. Yeah, works correctly. And when we reach, here we reach FF, this value here should be incremented. Yeah, so the counter works. Counter works just fine. And finally, I only have to put up that code for printing text data. So let's just, for example, put this one in 65EO. So in other words, in 1225EO. 225EO. And already I still have the previous data here left, so I'll just delete this. And well, this current data, where does it end? It checks here the if false, then we have keep text open, to write text. it ends here, and this thing here is leftover data. So I'll delete it as well. And we have to fill data here for printing the number in D004 and D005. And this works with in text code 09. And text data doesn't have to begin with 00. It could begin with any in text code. And here I'm using 09 to start the text data. And after it, we have the RAM address or pointer, and this has to be a 04DO because we have the higher byte first and the lower byte next as the number that is printed with this code. And next we have the byte. First 4 bits number of bytes to load, so the lowest bits, well, we want to load 2 bytes, so we set this as 2. And the first part, 0 don't care, 1 don't care, well, we can have this as 0, which is don't care. So this works. And after 09 code, how should we end this thing then? Well, this after this byte here, we can set any text code at all to start after it. And this 00 I want to stand for in text code 00. And here I only need 57 for stopping to look for more text data. So normally you could write like C I told you. And you end the text string with 57. I'm doing the totally same thing here. I'm starting the text data here for telling it to write a number from RAM in decimal and RAM address, which is D004. Tell it to write 2 bytes, and then I use another in-text code, which is in-text code 00, which has the possibility of ending text data with code 57. And I ended the text data with code 57. So this thing here is the text data for printing the number. I'd actually happen to write this see I told you code as well, which should be adjusted here. So E8 as the first byte, and 25 is 65 here. And I save it and decompile this one. And this is what PKSV shows this thing as. But if we now check it out with VBA and adjust D004 here in memory viewer and talk to this person event. Yeah, I want you to start counting the numbers. What? There's some problem here now. Because he's probably not loading the second byte at all, because he's just displaying 0 now all over and over again. or not the first byte at all either. Uh, let's see now. 09 and RAM address D004. Yeah, you should write this like any other pointer in the other direction. And this is because, well, you write pretty much everything in Little Indian format, and this is called Little Indian presentation. Big Indian would be D004, Little Indian is 04D0. And well, this byte had to be first 4 bits number of bytes to load. It probably means that the highest 4 bits are the number of bytes to load. So it had to be 20 instead of 02, I think. Let's just see about that. This works instead. And yeah, now it works. He is displaying the numbers correctly, like we wanted him to. And yeah, it loads each number as its own by printing 2 bytes starting at D004 and forming a decimal number out of them. And the counter goes on and on. I'm speeding it up a little bit. And each time this value reaches E8, it checks whether the value in D004 is 03, and if it is, it sets the bit 00, which is the first bit here. And this is how it goes. And again, reaching E8 and going off behind it. Or after it, how do you say it. But yeah, now we just waited for reaching E8 here, and you can see that this value still is 00, and it will be 01 when we've got E8 here as this value. Won't take long now. Yeah, counter stopped because this turned into 01 like we intended. And he says, see, I told you. If we talk to him again, this value is still 01, and here we have 03, 01. This turned into 01 because of it being used during this script data that was executed. For example, the yes or no command or such. We've got plenty of usable bytes here in the beginning of this D000. Or, well, yeah, here in the workram. For example, this one, this one, this one, this one, this one, probably this one too, and such. But yeah, with right byte codes, we changed these into 00s, and this one into 00, and it works, as you can see. 08 E8, and the counter ends. Yeah, that's pretty much about it. So let's just review. We've got this. We start off by changing these bytes into 0 zeros and this one into this bit into 0 for starting the counter. If we print the value, we increase the value here, and if this one reaches 0 from FF to 0, we increase this one instead. And each time it is checked whether this value is set to E8, and if it is, we check if this value is set to 03, and if so, we set this bit through assembly. And we print the value with this code from ROM, and wait for a little moment. And if this check passes, so if we have the first bit set, bit 00 set, it tells us, see, I told you, and the script ends. Yeah, that's how this thing works, pretty much. Next time, let's see what I have planned for the next time. As you can see, I have this plan of this counter here. Yeah. Next time, I'll be going to a little bit of program counter and stack and some other instructions that can be quite useful. And we'll be playing around with these probably then, and not doing anything about scripting, I think. At least I have no plans for bringing scripting to the next part, because we've pretty much gone through everything already, and the stuff related to it is something you should be able to study on your own. And yeah, that's all about it for today, and I hope you enjoyed, and